Welcome to this video on algorithmic persuasion with evidence. I'm Martin Hoefer, and this is joint work with Pasin Manurangsi and Alex Psomas. So in this work, we study an elementary game of persuasion between a sender and a receiver. So persuasion is a prominent topic in economics, and usually you have an agent that has information about the state of the world and another agent who can make a decision. So here S, the sender, has information about the state of nature, and R is the decision maker. And now the goal is to influence the decision maker, to reveal information, to disclose information in a way to influence the decision maker to make a decision in one's own favor. So here we study an elementary version of this, and the sender wants to persuade the receiver to change the status quo. So examples of this could be, for instance, the sender is an attorney and wants to convince a judge to convict the defendant. Or the sender is a job candidate and wants to convince a firm to hire her. Or maybe the sender is a consultant and wants to convince another company to acquire a new product. So the incentive or the preference of the sender is pretty clear here. He wants that the receiver change the status quo. On the other hand, the receiver wants to make a correct decision in a sense. So the state of the world comes in one of two classes. So either acceptable or rejectable. Where acceptable means the change of the status quo is good. So the defendant is guilty, the job candidate is good, we should hire her, or the new product is great, we should acquire the new product. Or rejectable, in which case it's not good to change the status quo, right? So this is an elementary game, very elementary, very basic. So the receiver just has two actions, accept, reject. The sender just wants the receiver to do a single action all the time, no matter what the state of the world is. And certainly you could envision more complex games, and more complex scenarios have also been studied in the economics literature. So let's make things a little bit more formal here. So the state of the world is drawn according to a given probability distribution D, and D is public knowledge for both agents. Now the sender wants the receiver to accept no matter what. And the receiver wants to make a correct decision, so he wants to accept if the state of the world is acceptable, and otherwise he wants to reject. Now, what do the agents do? They determine a strategy or a scheme, and the sender determines a signaling scheme to disclose information about the state of the world. And the receiver, getting this information, then determines what to do. So he determines an action scheme that maps the information that he gets, the messages that he gives, to an action. So the sender has the information. The sender sees what the state of the world is. He sees, or she sees, her own qualifications here, maybe in this job market example, and sends a signal. So sends maybe grades or a message to convince the receiver that the status quo should be changed, that, for instance, she should be hired. The receiver does not know the state of the world, but he knows the distribution, and he knows what the sender is doing and what the sender is saying. So he receives the signal, knows how the signal is generated, and then takes an action based on his action scheme. Okay, final utilities, according to the preferences of the agents. Utility of the sender is always 1 if the receiver accepts, 0 otherwise. Utility of the receiver is 1 if he accepts and the state of the world is acceptable. It's 1 if he rejects and the state of the world is rejectable, and 0 otherwise. Right. So that's a very elementary game, and you're welcome to take a minute and stop the video and think about how this game would be played, what would be an equilibrium, what would the agents do. So it's very simple. Now, what complicates matters in our scenario is the following restrictions: that signals are not arbitrary. So the agents cannot send arbitrary messages, but here we consider persuasion with evidence, as studied by Glaser and Rubinstein in Econometrica in 2004. Where each state of the world comes with certain evidence that cannot be forged. And now I can reveal part of the evidence, or I can choose not to do so as a sender. So this evidence could be like grades, test scores, maybe in academic scenario papers, or maybe if you have a product, then maybe there's experimental results or things like this on the performance of this product, on the performance of this tool maybe. And this is what you can disclose to the receiver. So more formally, we have a set of states of the world. Each state of the world comes with a probability from the prior and the label, whether it's acceptable or rejectable. Here, acceptable, I marked it in green. Then we have possible signals. These are the collections of evidence that can be revealed to the receiver. So these are the signals. And then we have this state signal graph that indicates in which state of the world can I send which signal. Right? And this is the input to our problem. So this is the restriction we're given. We cannot send arbitrary signals in any state of the world, but we have to respect this evidence condition that we have to give concrete evidence on the state of the world. Okay, so now in this case, what would the sender do? The sender now needs to determine to which evidence to send in which state of the world. So this could be, for instance, a signaling scheme for the sender. Here, he sends this signal here. In this state of the world, he sends also this signal. Then here in this state of the world, he mixes 50-50 with the middle signal and the right signal. And then here for the right state of the world, he sends the middle signal. All right. Okay, this would be a signaling scheme. Then the receiver would come and would see these signals and would determine, so what am I going to do now? All right, so for instance, if I get this left signal, what's my preference? What should I be doing? And here we can see, okay, if I get this signal, I get this signal in 30% of the cases, then 20% is this state of the world, 10% is this state of the world. So in two-thirds of the cases, when I get this signal, it's a rejectable state of nature. So my best response as a receiver here would obviously be to reject, because I would be correct 2/3 of the time. Same reasoning for this one. Here, this signal is sent half of the time. So in 0.5 of the time, we send this signal, and then with 20% it's this state, with 30% it's this state. So in 3/5 of the time it's a rejectable state, 2/5 of the time it's an acceptable state. So here also the best response would be to reject. Then for this state, for this signal here, it's clear that it's only being issued when this state of nature is there. So here, obviously, the best response is to accept. All right, so this would be the answer of the receiver here. All right, so now, given this classification of the receiver, given this action scheme of the receiver, the sender says, well, am I gonna stick to my signaling scheme, or is there a better way to signal? Now, given that the receiver does this, the incentive of the sender is, of course, to maximize the probability that the receiver plays accept. Now here, for these two states of the world, an accept is unreachable because both incident signals are being rejected by the receiver. For these two states of the world, there is actually an acceptable signal here, which is this one. So the natural incentive would be to maximize the probability that this signal here is issued. And indeed, this would be a best response here. And it also keeps the preference of the receiver. So here the receiver sticks to rejecting. Here he is indifferent because this signal is never issued. So we can assume that he also picks reject here. And then here he sticks with acceptance because the probability mass coming from this acceptable state is larger than the one coming from the rejectable state. Okay, this would be in a sequential equilibrium here. And the sender utility would be 0.7 because 70% of the time this signal here is sent, it's being accepted. The receiver utility would be 0.6 because he's correct 60% of the time. So 40% of the time here, right? And then 20% over here. So this is how he sort of manages to correctly identify the label of the state of nature. It's not the only equilibrium. There would be another equilibrium like this, for instance. Here, the sender simply sends always this middle signal. Then the receiver is indifferent. It's 50-50 between accept and reject. So we could assume that he always plays accept for all these signals. So he always chooses the accept action. That of course makes the sender happy. Now everything's always accepted here. Receivers correct 50% of the time, but this is also the best you can achieve given this signaling scheme. So the equilibrium is not necessarily unique, and there's different equilibria with different values for sender and receiver. Okay, so that's what we study in this paper, and in particular we study this from a computational perspective. So the goal is to find a pair that's a sequential equilibrium. Then, in addition to this equilibrium problem, there are other versions of this game that have been studied in the literature, in particular ones with commitment power. So in the economics literature, a common assumption in the area of Bayesian persuasion is that the sender has commitment power. And he commits to a signaling scheme in advance, and then the receiver best responds to it. But because he has committed in advance, he's not best responding to the receiver directly. Rather, he's anticipating the best response of the receiver. So in this sense, it becomes a bi-level optimization problem where the sender tries to optimize his signaling scheme, taking into account the subsequent best response of the receiver. Same goes for the receivers. If the receiver's commitment power, he commits to an action scheme in advance, and then the sender best responds by presenting a signaling scheme, and then the receiver has this bi-level optimization problem where he tries to find a good action scheme, anticipating the best response of the sender. Now, there's an endless debate in the economics literature whether these commitment assumptions are actually justified. I think there are examples where these sound plausible. So for instance, if you think of an attorney who designs his signaling scheme, who designs his accusation strategy, taking into account the best response or the behavior of the judge, that could be modeled by a persuasion problem with commitment power on the sender. If you think of a company who says, okay, here is criteria based on which we would hire a new job candidate, and now the candidate tries to find evidence or grades or test scores in order to meet these criteria, that might be a case where we have the commitment power on the receiver. But in general, like I said, there is debate when and whether these can be applied. But here we study these problems from a computational perspective. We're not necessarily going into details about like economic details of this application. Okay, so what can we say about this? First thing is equilibria. A sequential equilibrium can be computed in polynomial time in general. So you give me an instance of this persuasion problem with evidence, and then there's a polynomial time algorithm to compute a sequential equilibrium. So I didn't flesh this out here in the context of this video. So the main takeaway from these 4 lines is that we have a max flow based technique that iteratively determines whether signals should be accepted or rejected, and computes corresponding signaling and action schemes. If you want to know more, I'm happy to answer your questions by email or come to me during the conference, then we can talk about this. If we look at these commitment power variants, turns out that both agents can substantially improve their utility over the one obtained in an equilibrium. So commitment power actually has a benefit can have a substantial benefit to both sender and receiver. To illustrate this, here are 2 examples. So here is a scenario with 2 states of the world. One is acceptable, one is rejectable, 2 possible signals, and the signal state graph like this. Now, suppose the sender has commitment power, and suppose he commits to this signaling strategy. Then what is the receiver doing? The receiver sees on the left side it's 50-50 here for this signal, 50-50 for this signal. Obviously, it should be rejected because there's only rejectable states of nature behind it. So this would be a best response of the receiver, where here we always assume tie breaking in favor of the sender to avoid messing here with small epsilons to make strict preferences. So here for the sender commitment, we always assume that the receiver breaks ties in favor of the sender, which here, of course, means that he would pick accept. He could also play reject, would have the same utility, but tie breaking in favor of sender means that he's accepting this signal. What's the utility? The utility of the sender here is 0.8, obviously, because in 80% of the time the receiver accepts. But as can be easily seen, this is not an equilibrium, because here there is an accept signal. So obviously the sender has an incentive to send this signal as often as possible. Essentially all the time. I mean, he can send the signal all the time, but if he sends the signal all the time, then of course the receiver would say, okay, now 60% of the time I'm getting a rejectable state, so I'd rather pick action reject here. And indeed, by applying this reasoning, we can see that every equilibrium in this instance has the receiver reject both signals. So in every equilibrium, all signals will be rejected. The receiver always plays reject. So the utility of the sender is 0. So here we see that the sender has a massive advantage if he enjoys commitment power. I mean, the ratio here between these two utilities is unbounded, but also in terms of absolute difference, it's a pretty substantial improvement. Similar observation for the receiver. Now here is an instance where we have again, two states of the world, two signals. The state signal graph is a little bit different. And now suppose the receiver commits to this action scheme. Then the sender tries to maximize the probability that the receiver accepts. But given this restriction in the graph up here, that's the best he can do. And turns out that this is also an equilibrium, right? So this gives a perfect information, perfect classification for the receiver. So he perfectly identifies the acceptable and rejectable states. But also it's an equilibrium. So if you see, then of course the receiver is happy and the sender is playing a best response. So here we also have an equilibrium. And that's actually a general result by Glaser and Rubinstein, that the optimal strategy for the receiver with commitment is also part of an equilibrium. So there's always an equilibrium in which the receiver plays his optimal strategy with commitment. What about the worst equilibrium? So there's of course other equilibria. Here's another equilibrium. The sender simply sends this signal here all the time, and the receiver always rejects. It's easy to see that this is both of these things are best responses. So that's an equilibrium, and here the receiver is only correct 50% of the time. So his utility is 0.5. And so this gives a factor 2 improvement with commitment over the worst outcome without commitment. And this is actually tight. So we proved this in the paper that the factor of 2 is the worst case for this ratio. Okay, so punchline here is the sender can improve possibly substantially. The receiver can also improve by a factor of 2, up to a factor of 2 with commitment power. So let's study these commitment power versions. Let's see what we can show for that. Okay, so in the paper, we first study the general scenario of these two problems, and it turns out that persuasion is, in terms of approximation, the harder problem, I would say. So we have an upper bound on the approximation ratio of O of n, but we can also show that this is independent set hard, so it's n to the 1 minus epsilon hard for any constant epsilon. The delegation version where the receiver has commitment power, there's an upper bound of 2 and there's a lower bound of 2 minus epsilon in approximability of 2 minus epsilon for any constant epsilon. Okay, so these upper bounds, these algorithms, they're really simple, and turns out that asymptotically they have the optimal approximation ratio in the general case. So even though this scenario seems very elementary from the outset, the restriction to evidence can make this pretty hard, this problem. So we also studied more structured cases where we have, for instance, a unique acceptable state or a unique rejectable state. These cases allow much more positive news. So for both of these scenarios with unique acceptable state or unique rejectable state, we can solve the delegation problem in polynomial time. For the unique accepts and persuasion, we have a pitas and strong NP hardness. Unique rejects can be solved in polynomial time also for persuasion. And then there is a condition termed foresight, which was introduced by Scher in Theoretical Economics in 2014. And I don't have time to go into the details of what instances with foresight satisfy. What's the structural condition here? But that's actually a condition that can be applied here to unique reject. So unique reject is a special case of instances with foresight. So this algorithm here is actually a consequence of a result proved by Scher. The algorithm by Scher is also a max flow based algorithm, but for persuasion, it's not useful. So for persuasion, even instances with foresight can be very hard to approximate. So we also studied restrictions on the state of nature, so in particular degree restrictions. So these restrictions don't really make the persuasion problem any easier, but they have an impact on the delegation problem. So here degree 2 states means that every state of nature, we only have 2 possible signals. For degree D states, it's a natural extension to degree D. Degree 1 accepts means every acceptable state has degree 1. So for every acceptable state, there's a unique signal to send. Degree 1 rejects for every rejectable state, unique signal. For degree 2 states, we have this 1.1 approximation, APX hardness. Degree D states, we have a sort of progression that goes to 2 as D increases. Degree 1 accepts is again a special case of this foresight condition. And for degree 1 rejects, we have APX hardness and we can show the lower bound in terms of inapproximability, but the upper bounds, improved upper bounds, especially for delegation, is an open problem. I can't go into detail on all of these results, so that's why I will focus on one of them, which is this 1.1 approximation here for degree 2 states. Okay, so degree 2 states, every state is connected to at most 2 signals. So here's an example. And now what we do here is we develop a new representation where we say signals are vertices and states of natures become edges. So we turn each of these states of natures here into an edge between the corresponding signals. And these new edges are, of course, weighted by the probability that the state of nature is drawn. And they're also labeled accept, reject based on whether the state is acceptable or rejectable. So then this graph becomes this graph. Now, from the literature, especially from Glaser and Rubinstein, we know that the optimal solution for the delegation problem is deterministic. So in an optimal solution, or there is an optimal solution where the receiver labels each signal deterministically whether he accepts or rejects. Right? So in our representation here, that means that the receiver essentially labels each vertex either acceptable or rejectable, so either A or R. So let's assume he does that, for instance, like this. So here this signal becomes accept signal, these two become reject signals. Now, given this labeling, the sender plays the best response and has an incentive to assign as much probability, as many states of the world to the accept signals as possible, to send these accept signals as often as possible. So what the sender will do, it will assign edges to A vertices whenever possible. Right? So all of these edges here, the 0.2, 0.1, 0.4, they're all going to be assigned to this vertex, which means that in these states of the world, he's going to send this accept signal. Here, for this state of the world, he doesn't have an incident accept signal, so all he can do is send a reject signal. Right. Okay, so this is what the sender is doing. Now, what's the objective of the receiver? What's the objective function here is, of course, his utility. And his utility now is the weight of all accept edges with at least one incident A vertex plus the weight of all reject edges with 2 incident R vertices. Right, so obviously, the sender tries to send the accept signals as often as possible, and that's fine as long as there are acceptable states of nature, right? So for these states of nature, it's actually fine to send a signal because they get correctly classified then. For this state of nature, the receiver would prefer to get a reject signal, obviously, but since the sender maximizes the accept probability, this will be wrongly classified. Here, this state will also be correctly classified because it will go to will be assigned the reject signal, and then sort of the receiver takes the reject action. So this is correct as well, right? So after going through all this reasoning, we see that we now, putting ourselves into the shoes of the receiver, want to label all the vertices in a way to maximize this objective function, to maximize the weight of all accept edges with at least one A vertex, with at least green vertex, plus all reject edges with 2 incident R vertices. Okay, so how do we do this? Well, a way to do this, or a way to formulate this optimization problem, is the following integer program. Now here we assign for every state / vertex a number, xi, and xi is -1 if the signal becomes an accept signal, if the receiver does accept in the signal, and it's +1 if the receiver does reject. And then we can go through this equation here and see what happens. And we see that for these acceptable states of nature, this expression here becomes 4 exactly when at least one of the incident signals is an accept signal. So if at least one of xi or xj is -1, then this thing here becomes a 4. Otherwise, it becomes a 0. Same thing over here, or according thing over here, where we have the rejectable states of nature, and this becomes 4 exactly when both of these xi and xj are +1, so both incident signals are reject signals. Otherwise, it becomes 0. All right, and then we divide this by 1/4 here, and then we have the probability mass of the correctly classified accept states and the probability mass of the correctly classified reject states. Okay, so we don't solve this integer program directly. Instead, we come up with an SDP relaxation. And so we solve this SDP. We round the solution to an integral 1. So here, what we do is we adapt rounding techniques that have been developed for SDPs, for instance, for the Max-Decart problem or the Max-Tussard problem. These are the corresponding references. So here we need to adapt these techniques, and these techniques have certain parameters, and we did an extensive search in the parameter space and proved that with these parameters that we found essentially by brute force search, our algorithm has an approximation ratio of 1.1 at most. So it's not clear whether this is tight, whether this is the best ratio. So this is the best we could find using these techniques and a pretty exhaustive search in the parameter space. Okay, so this was essentially all that I wanted to talk about. So let me conclude. So what we study is an elementary scenario of persuasion with signals restricted to evidence. We show algorithms for computing sequential equilibria efficiently, and we also show approximation algorithms when agents have commitment power. And in terms of approximation, this is the general picture that we have. So the persuasion problem seems to be generally harder to approximate than the delegation problem, but also the delegation problem is hard in general up to trivial factors. And we identified a number of structural conditions under which we can show improved approximation results. And that was it. Thanks for watching.